This is 3.4. This is going to be a section that is following up on finding maximums and minimums, and we're kind of taking this to the next step. We're going to talk about concavity and points of inflection. So let's first talk about what concavity means. So concavity is describing the shape of what a graph looks like. So if you see right here, okay, this graph right here is concave upward. Okay, so it's concave upward because it kind of looks like a bowl. So it's really, I guess, hard to explain. You just have to understand the concept of what concavity means, and seeing that because it's looking like this, that means it's concave upward. And then this graph over here is just saying that we're concave downward. So what happens is, we talked about maxes and mins, and we've talked a lot about derivatives. And we've used derivatives to find maxes and mins because the derivative describes the slope of our function. So like if we were looking at this function right here, if this is our f of x, we would say that our derivative is positive when our function is increasing, and we would say our derivative is negative when our function is decreasing. The concavity of a function is determined by the second derivative. So where we say if the first derivative is positive, it means the slope is positive. If the second derivative is positive, that is what will give us a concave upward portion of our graph. So anywhere where you see that this is concave upward, that means that the second derivative is positive. And then wherever you see where the graph is concave downward, that is where the second derivative is negative. So it's going to be very similar to what we were doing when we found maxes and mins to figure out the changing slope. Is we're going to use graphs and second derivatives to figure out when our graphs are concave up and concave down. The second piece of information is called point of inflection. And point of inflection is just the place where a graph changes concavity. So if I were to draw a real quick graph, and you see what I just did here, this graph is concave up all the way until about this point right here where it changes to concave down. This is what we call a point of inflection. And that's going to be important because when we find maxes and mins, we were setting the first derivative equal to 0. To find points of inflection, we're actually going to be setting the second derivative equal to 0. So what I want to do is just run through an example here. Now keep in mind, for the most part, you don't need, this is a pretty tough function to take a first and second derivative. So I am going to skip steps. I'm just using this as an example to show you how this will work. So what's going to happen is we would take the first derivative of this function, and we would have to use, you could either use the chain rule by bringing this to the top, or you could use the quotient rule with the, because we have a quotient going on here. So in the essence of saving time, I am not going to go through the entire quotient rule. What I'm just going to do is show us what the derivative would be. I'm just going to write it straight out. It's going to have the quotient rule involved in it, but I just want to show you without having to go through. I don't want to rehash figuring out how to do the quotient rule. So we have 0 times x squared plus 3 minus 6 times 2x. And all of that is going to be divided by x squared plus 3 to the second power. And that ends up equaling negative 12x divided by x squared plus 3 squared. So that's our first derivative, is f prime of x. And again, we would use that if we were trying to figure out our maxes and our mins, and we could still do that. So now what we're going to do is we're going to find the second derivative. And again, I'm going to do this very quickly, skipping a couple steps here. We would have to do the derivative of this, which would be the quotient rule again. Okay? And what you end up with here is, I'm just going to go straight to the answer here, is we end up with 36 times x squared minus 1 divided by x squared plus 3 to the third power. So this is our second derivative. So this is what we're going to be, that's the function we're going to be using. So now keep in mind, we want to know when this is equal to 0. So when is our f double prime of x equal to 0? Well, that is where we set the top equal to 0. because the bottom does not mean that we're going to get zeros. Remember, for a fraction to be 0, the top has to be 0. So essentially, we're going to factor this x squared minus 1, and if you recall, x squared minus 1 will factor to be x plus 1 and x minus 1. So f double prime of x is equal to 0 when x is equal to negative 1 and x is equal to positive 1. And guess what? That means that x equals negative 1 and x equals 1 is our points of inflection. That is where our graph is going to change concavity. But now what we want to do is we also want to determine the intervals of when the function is concave up and concave down. So what's going to happen here is we're going to do our number line exactly the way we did when we did our maxes and mins, except now we're going to use f double prime instead. So we're going to plot negative 1, and we're going to plot positive 1, and then we're just literally going to see, we're going to plug in values into our second derivative. I'm going to plug a value to the left of negative 1 into our second derivative. If it's positive, then it means it's concave up. If it's negative, then it means it's concave down. So we plug in something to the left of negative 1, and again, in the essence of saving time, I plug negative 2 in, and I actually get a positive value. Then I plug 0 in, number in between negative 1 and 1. I get a negative value, and then I plug in 2, and I get a positive value. So what does this mean? What we're going to do is we're going to label this as such. And I'll label it in a different color so you see. So first of all, we're labeling our points of inflection. Our points of inflection are x equals negative 1 and x equals positive 1. Then we want to label when our function is concave up. Concave up is where our second derivative is positive. So what we're going to do is we're going to use that interval, the interval notation that I showed you a little bit in the last trimester. So we know that it's going to be from negative infinity all the way to negative 1. So I just say negative infinity to negative 1, and from 1 to positive infinity. Now remember, these are not coordinates, these are intervals. The parentheses just mean that the numbers are not included, so we're just saying this means from negative infinity to negative 1, and from positive 1 to positive infinity. And then for concave down, it's just going to be in between negative 1 and 1, so we're going to say negative 1 to 1. And we just write it in this notation. So that is what this problem is asking. It's looking for the points of inflection, which we found by setting our second derivative equal to 0 and solving. And then we figured out the concavity by plugging the intervals into our second derivative to see whether we get positive or negative, and then we can write out our intervals. So that's how you'll do all of these problems. You'll take the second derivative twice, second derivative, set it equal to 0, find your points of inflection, and then check your intervals to see if they're positive or negative. So I want you to try this one on your own. Let's see how you do, answer the question, and hopefully it makes sense. And this is a pretty easy function for you to derive. So try that and let's see what happens. So taking the second derivative in this one, you should have gotten x equals 0 and x equals 2, which makes that your points of inflection. Then what we did was we plugged our intervals of each of these into our second derivative, and you should have gotten positive to the left here, negative in between, and positive to the right. So when you write your intervals, we have from negative infinity to 0 is concave up, and from 2 to positive infinity is concave up. That's where these intervals come from. And then our concave down is in between 0 and 2. So we just write our interval as 0, 2. So hopefully that makes sense. If you have questions, obviously bring those to class, and I will see you then.